Oh, okay.
Yeah.
Let me know when we are live, Alfie.
We're live, I think.
Oh, awesome. Hello, everybody. It's very nice to have all of the participants now in today's market assessment session of the Women Empowerment Online Conference. I can see about 16 participants now. I'm very thankful to everybody who's joined for today's session. Just to let everybody know that we'd had a very nice and interactive session last weekend, which was about measurement working group, education working group, and technology working group, which was on the last weekend. All the session were video recorded and has been now uploaded in the Women Empowerment website. So anybody who's missed the last session can now see the recorded video by going into the Women Empowerment website. So for today's market assessment session, Alfie Alsop and myself, we will be co-hosting today's session. The session will span to tentatively a length of 1 hour 45 minutes, followed by delivery model session. We think that the market assessment and delivery model goes quite closely hand in hand together. Therefore, we've planned both of the session to be carried out on one day. In fact, actually, we've planned for a shorter discussion time after the market assessment presentation, so that we can integrate a broad discussion between market assessment and discussion. Joint session during the end of today's conference, so that we can actually do a lot of discussion about different aspects which have similar discussion topics. I will be starting with a brief introduction to Women Empowerment Market Assessment introduction, along with some of the end user survey that we did with the market assessment in Nepal a few years back, which was on 2017. And then followed by that, Alfred will be talking much in detail about the market assessment Women Empowerment methodology. And we have two very, very experienced, I should say, presenters today. We have a presenter from CIAMAT, Center for Energy, Environment and Technology Research from Spain, Mr. Luis Arribas. His work is focused on specification, sizing, and assessment of renewable energy system. And we have a follow-up presentation after that from Jose Armando, who is based in Peru. His work is mostly concerned with developing renewable energy projects in Peru, and also a co-founder of Microgrid for Sustainability organization. You'll be hearing a bit more about their work in detail during the presentation. Also, the session will be recorded, so expect the online, expect it to be available in few days, again in the Women Empowerment website. That was a very brief introduction to today's session and about our presenters. Alfie, do you think I missed on any points?
No, I think
my presentation now.
I think you covered it all perfectly. Thanks, Kimon.
Oh, awesome. Okay, so I'll get started with today's session now. Okay, so today I'll be talking about introducing briefly about the market assessment for small wind power and the results of the end user survey. So end user survey is one of the components of a broad assessment that happens in a market assessment project, and the one that we did was with solar wind hybrid system in Nepal. Just before continuing my presentation, just want to introduce myself. I'm a electrical and electronics engineer passed out from Kathmandu University in Nepal, which was in 2010. I worked with Kathmandu Alternative Power and Energy Group for almost 9.5 years, actually, which was actually mostly with design and construction with small wind turbines, a little bit with micro hydro projects and pico hydro projects, mostly with electricity access in remote off-grid areas of Nepal. And most recently, it's been a bit more in the last couple of years, it's been mostly with clean cooking technologies in remote off-grid areas, and feasibility studies and assessments, mostly with renewable energy systems. And I joined Wind Empowerment Board in 2018 in the position of secretary during the Wind Empowerment conference in India. It's been very interesting working with the Wind Empowerment Board. And currently I'm doing my research master's again in, it's been a bit more technical now in the area of small wind turbine control. I'm currently based in South Africa. So starting with market assessment. What is market assessment? It's a holistic process that aims to establish how suitable a product or service can be in a given context. And when I say given context, it is actually, there are different, different regions in different countries have different circumstances and conditions. And it's about, how a, particular product or service can best match a user's need. But it's also about quantifying the potential of a product and service and highlighting the most effective ways of reaching the potential. But what I should say Alfie and myself has found out in the last few years is that whenever we talk about market assessment, people think that it's purely an economic exercise, but rather it can't be further away from the truth, because it actually wants to study the entire ecosystem of where a product and services is actually, where its position is in terms of investigating the policy, supply chain, finance. And so at the end, what we want to know is where can small wind turbine contribute? How can it contribute, and what can be done to maximize its contribution when we talk about rural electrification with small wind. About the methodological steps, Alfie will be diving in much deeper on each of these steps, but let me just go very briefly about it. So it starts with learning from previous experience, which actually is studying past previous projects, doing some literature review. It involves key stakeholder interviews and also end user surveys, from which we want to know what things has worked, what things has not worked from the past projects. We want to know the common concerns from key stakeholders. The second step is geospatial techno-economical modeling, where we use two different softwares like GIS mapping tool and Homer Pro Simulation software to quantify the size of the market by different energy mix and know how many wind turbines or whatever the energy mix is in the most cost optimal way. And mapping the energy ecosystem is actually about combining all these results from the previous steps to finally be able to say that these are the list of solutions that one may be able to recommend at the end, but also addressing different barriers and different obstacles that comes along the way. What can be considered as a good market assessment? Different competing services. For example, a location or a region could have good solar resource, or it may have good wind resource. How does these different resources or services can compete with each other? What's the size of the demand? What's the technical potential? And what's the enabling environment like within these landscape? Previous market assessment project for small wind power that the Wind Empowerment has done actually is, so it has carried out market assessment project in Nicaragua, Ethiopia, Malawi, and the detailed project report, you can find it in WIN Empowerment website. But most recently, a publication has been done, which actually critically reviews the market assessment methodologies and discusses about the niche context where small wind turbine can make a valuable contribution for off-grid electrification. The last market assessment project was carried out in Nepal, with collaboration with Alfie from Wind Empowerment. Also, the document is can be found. The final report can be accessed from CAPEC website. Just another thing worth mentioning is about the global market assessment for small wind, which was again another project carried out by Wind Empowerment, which discusses the methodology on how the information and results are processed in order to achieve robust ranking system for all countries, and highlighting those with highest favorability for small wind technology. So if anybody is interested to read about it, you'd be able to find it in the Wind Empowerment website again. With that introduction to market assessment, just want to dive into the end user side, which was what I mentioned, one of the aspect of assessment that we did during the market assessment project in Nepal. So it's, I think, worth pointing out in the beginning that when we started the market assessment project, is a couple of locally constructed wind turbines project that was carried out by Practical Action over the years. So it was actually, the number of installations was 15, but none of the wind turbine system is operational. Some failed in a couple of months after installation, some failed over a few years. There are different issues actually that exist, why they failed. So, but still at the side, there's been a lot of work that has been implemented by a government institution called Alternative Energy Promotion Center, which has implemented a lot of commercial commercial wind turbine system in hybrid mix with wind turbines. So the end user side assessment actually investigates mostly with these hybrid installation sites, which we explored. So here you can see a map with 6 installation sites. We made sure that we visited the installation site, which was geographically very diverse, to understand what kind of issues existed, what was the actual situation. So this is one of the installation site, which is 10 kilowatt wind, 5 kilowatt each unit with 15 kilowatt solar. So after 2 years of installation, the complete battery bank was damaged because of overcharging, and what we suspected was one of the problem with the controllers configuration. So the agency, actually Alternative Energy Promotion Center, replaced the batteries, but the wind turbine, one of the unit, stopped working after 4 years. So it's been operating now with limited operation. By limited operation, I mean the electricity is not provided across all hours of the day. So there's some load shedding, but very little access to electricity. Is another interesting thing that we found with the installation site at this village called Dhawari, which is 10 kilowatt wind, 5 kilowatt each unit, and 2 kilowatt solar. This is also quite interesting because the inverter failed after 5 years, and the committee did not, the village committee who was responsible for the operation of the system, did not had enough money to buy the new inverter because it was not possible to do the repairs. And so that challenge has had to be dealt with by the assistant from the government agency as well. And then after 7 years, one of the blade failed, and to repair the blade actually took one entire year to have it back to the site and operate it again. So there's a long mean time to repair that we are talking about, and lots of issues. Another interesting site was Harekana, again at the far west region of the country. This site is so remote. It takes about 2 days to reach this installation site, but you have to pass through a national reserve, and so you can't travel alone over there. You've got to be with a couple of people because it's not safe. So there's lots of logistic issues when you're talking about the installation, but during the installation, but also for maintenance also it's a lot of issue. For instance, one of the picture at the bottom, you'd see the solar panel has been broken, but there's no during the assessment time we found out that there's the system is not likely to be repaired in the future. But also another thing that's worth mentioning is, I think, the operator, because the first operator who worked in that installation site was trained, but because of the low salary issues, he went outside the country, and so there was no operator actually, and just one person who knew very little about the system was working as a operator. This is another very interesting site which actually failed 3 months after the installation, and this actually clearly reflects on how lack of standards and installation guideline can affect the component sizings and specifications. And actually the failure was again in the inverter side, where the lightning caused the damage, but yeah, it affects the has a very big effect on social kind of thing, because in such a early stage of its operation, when you see those kind of failures, it's very damaging in terms of social perspective. Another very interesting site was Hariyarpurgadi, which is got 10 kilowatt unit each wind turbines and 15 kilowatt solar. This particular site is a bit interesting because it was implemented with a new operational model, which ensured that at least 3 years of maintenance service was provided by the installer, but also 2 preventive maintenance visits each year. So in most of the sites, what we identified, we tried to plot the system lifetime, and what we found out was actually after a couple of years, you compromise a lot because of the maintenance issues with the batteries lifespan, and so which actually ends up restricting the electricity access, and so at the end it's very little that you can do with such big systems. Just to give you a bit of a visualization about the repair and maintenance scenario, here you can see different installation sites in the color with icon yellow. Probably you can see the icon of wind turbine also, but the one in blue color icon is the installation, is the installer location. So in such a geographically diverse country, when you've got such a small industry around a specific technology, it's very difficult to secure a very secure, reliable, and low-cost service because it's so difficult in terms of accessibility. So I've touched a bit on system operator. Is a clear issue of revenue because the kind of money that is accumulated over the year is not going to be enough to do a long-term replacement for, let's say, a very significant cost-carrying components like batteries and inverters. And so it's kind of a difficult issue in that particular subject, and it's one of the things which we will talk about a bit more during the discussion session. And what about the productive end use? Because clearly it's when we're talking about rural electrification in developing countries, clearly the affordability is one of the key issues. And so is it really possible to, see a productive end use? What kind of productive end use actually exists at the sites? We can see some, grinding end users, but its size is quite high. And so a clear issue is that, scalability of this kind of productive end users with these battery system. Only one side where we were investigating had a couple of small size wood, factories and a small grinding machine, but still the same problem of scaling these kind of productive end users. So at the end, it's the matter of what happens when there's a good maintenance and when there's no maintenance. A no maintenance situation or poor maintenance, let's say, leads to reduction in electricity quality and duration over time. And so this leads to people not wanting to pay for the electricity, which is what we saw during this end user survey. And so there's very little chances of productive end users with this situation, which in turn means that there's no money for maintenance. So it's kind of like a vicious loop that starts with no maintenance, and then again there's no money. It's kind of like a quite difficult situation. Another quite interesting subject is product quality versus maintenance. What about the product quality? Because if you are trying to put up a system with high product quality, means that the capital cost is going to be high, and so what's actually the right spot for having a minimum quality, but also at the same time securing that it's sustainable with particular techniques, like maybe going for reactive maintenance, going for the preventive maintenance, so that you can make the project system lifespan as long as possible. But that's quite interesting because it's not as easy as it sounds. And these are a couple of other questions that Alfred will be touching upon during the discussion session. This is one of the few that we can definitely talk about. And I think that ends my presentation. And also I forgot to mention that we will take in questions at the end during the discussion round. Alfie, are you there?
I'm there. Thank you very much, Kimon. I will start sharing my screen. And just to reiterate what Kimon just said, we will be answering and addressing any questions. I see there are quite a few already at the end during the discussion session. So just now I will share my screen and begin my presentation. 1 second. Okay, so hopefully you can see my presentation now. There we go. Can you see that?
Yep.
Perfect. Okay, so thank you everyone for joining us today. My name is Alfie Alsop, as Kimon kindly introduced me. I've been part of wind empowerment for the last 4 years, since the conference in Argentina and just before that. And for that entire length of time, I've been working with the Market Assessment Working Group, pushing forward the methodology of the wind empowerment market assessment. So the purpose of this presentation is to give you a little bit of background history on what the market assessment has looked like historically over different market assessments as conducted by wind empowerment teams, and what it currently looks like. And I'll go into a little bit more detail on what the assessment as it stands looks like. So I'll give a brief introduction, then I'll go through the market assessment methodologies used in Nicaragua, Ethiopia, Malawi, and Nepal very briefly. I'll spend a little bit more time discussing the current methodology, and then give some ideas about what future work might look like for the working group. So fortunately, I've got an easy job here because Kimon's already done a fantastic job of introducing market assessments. I think something to reiterate, though, is when we're talking about market assessments, the word market tends to bring people's minds to thinking about financial markets. You know, how much money, how much revenue, how much investment might this technology or solution draw in? That's part of what a market assessment is about. That's part of the question that a market assessment addresses, but it's by no means the end of the story. The whole of the story is, as Kimon said, how well the solution or the technology matches the needs of the end users. It's no good to consider, you know, the areas in a country that have sufficient wind speed for a small wind turbine if either nobody lives there, or the people who do live there aren't able to afford it, or if the people who do live there are already connected through other means, or if, for example, a different form of technology would be better suited to providing their energy needs. So why do we need market assessments? We need market assessments to highlight where we should focus our resources. We need market assessments, so both geographically and in terms of directed efforts. So when I say directed efforts, I mean what kinds of things need to change, whether that's in terms of policy, whether that's in terms of building technical capacity, or improving supply chains and so on. And then what can they tell us? Well, the first aim of the market assessment is to quantify the market. It's to give you a figure on how many people are best served by small-scale wind turbines within a certain area. That area could be a country, it could be on a global scale, or it could be within a handful of communities in a rural area of a developing country. The other thing that market assessments are designed to tell us is how can we improve the situation of small wind? How can we increase the scalability of them and make it more likely that they can compete in parity with other off-grid electrification technologies, such as obviously solar PV. The last question I've listed here is how has wind empowerment's methodology evolved? And that's what the next few slides will be directed at discussing. So I'll talk a little bit about the Nicaragua market assessment. Fortunately, we have John Leary participating in this call now. I wasn't involved in the Nicaragua market assessment or many of the other market assessments that I'll be discussing, but John was. So if you have questions on these, fortunately and hopefully John will be able to answer some of them. So the Nicaragua market assessment was conducted in 2012 to 2013, jointly between Green Empowerment, Wind Empowerment, Blue Energy and Pelican SA. So the aim of this assessment was to highlight, as I said before, where small wind can be an effective solution for off-grid electrification in Nicaragua. So the report and the study went to some detail in analysing maintenance patterns, the cause of failures, the business models used in different installations, stakeholder perceptions, and cost effectiveness. So when quantifying the market, the study in Nicaragua considered 5 different options. It considered grid connection, diesel mini grids, micro hydropower, solar PV, and off-grid small wind. And then some techno-economic modelling was performed to understand which of these solutions would be the cost optimal solution, as in the cheapest solution over its lifetime, for each location within Nicaragua. So I've put a link here at the bottom, realizing that you cannot click that link, but hopefully at some point we'll be able to share these in the chat so you can have a look at all of these reports. The Ethiopian market assessment was conducted in 2015 and 2016 in partnership between Wind Empowerment and Mercy Corps Ethiopia. It was commissioned by Mercy Corps Ethiopia to answer the question, what role, if any, could small wind turbines play in the electrification of remote communities in the Somali, Afar and Southern Oromia regions of Ethiopia? As part of the study, there was a detailed analysis of component availability, cost, and maintenance capacity, with a focus on the benefits of locally manufactured turbines as opposed to commercially available wind turbines. In the techno-economic modelling performed to quantify the market, there was consideration of 4 different options. A hybrid option of solar PV and diesel generation, a hybrid option of solar PV, small wind turbines and a diesel generator, small wind turbine and a generator, and then a generator on its own. This produced a map of the cost optimal solutions, which I'll share with you in a second. And this was the first of Wind Empowerment's market assessments to explicitly consider hybrid systems, so systems that are combining 2 different forms of generation. So on the left here, you'll see the cost optimal map of generation mixes for systems in Ethiopia. And I've put this side by side with a wind map of Ethiopia, just so that you can see the influence of wind resource. I mean, this is probably quite obvious for many of you, but where there is decent wind resource, there is more of a chance of it being the cost optimal solution. Obviously, there are so many other factors, but I've put these 2 images side by side just to demonstrate just how much decent wind resource influences that. So you really, from this, you can see that a large amount of the southern and eastern part of Ethiopia is quite suitable for small scale wind in hybrid systems. Just to quickly cover the Malawi market assessment, this was conducted in 2015 and 2016 in partnership with Wind Empowerment, the University of Strathclyde and Community Energy Malawi, with funding from the Scottish Government. So the study evaluates the viability of locally manufactured PV and wind hybrid systems for remote communities in Malawi. Again, I should highlight the fact that these are hybrid systems. These are not standalone wind turbine off-grid systems. As part of this methodology, there was a more sophisticated spatial analysis, a finer resolution of the final map, and a focus of different kinds of productive uses, including domestic uses, egg incubation, and maize milling for the end user communities. Unfortunately, and as is the role of market assessments, the conclusion of the Malawi market assessment was that the optimal systems for Malawi do not in general include small scale wind turbines. Through a number of factors, most of all being the lack of reasonable wind resource year round. So the conclusion of the Malawi market assessment was that solar PV is scalable and affordable, increasingly affordable, I should say, across the entire country of Malawi. The modularity and simplicity are ideally matched to the needs of off-grid communities. However, the promotion of small-scale, locally manufactured wind turbines in systems is not recommended. It would increase the levelized cost of energy in these systems rather than decreasing the cost, due primarily to the insurmountable barrier of limited wind resources scattered across Malawi. And this is something worth pointing out here. There are some factors that we assess in market assessments that can be overcome. For example, if a market assessment highlights a lack of technical capacity for maintenance for small wind turbines, that can be addressed. What can't be addressed, unfortunately, is a lack of wind resource. That's a point where we say, okay, we hold our hands up. It's not a feasible solution in this location. But that's an important outcome for a market assessment, because that lets us know this is not an area in which we should be spending resources, because it would ultimately be a waste of resources. We should focus elsewhere where small scale wind has a stronger chance of being an effective solution. So Kimon has already done a great job of talking about the Nepal market assessment. This was conducted in 2017 and 2018. It was a national scale assessment in partnership with Wind Empowerment, the Kathmandu Alternative Power and Energy Group, and the Alternative Energy Promotion Centre of Nepal. And it was funded by the Visions of the Wuppertal Institute for Climate. The study aimed to highlight areas of Nepal where small wind is part of the optimal solution, and then recommends the next steps to optimize the enabling environment. So building on previous methodologies, this introduces an even more sophisticated spatial analysis, the inclusion of geographically varying system costs, including geographically varying maintenance cost, obviously, as Nepal or many regions of rural Nepal are very remote, some of these sites taking 2 days to visit. Maintenance costs just for the transit between maintenance hubs and sites can be quite high. So we recognized the need to factor this into our technical and economic modeling. And also these systems have been scaled to population. So the demand present at each location, we have scaled to the population living in that area. And I'll just show you these two maps. So the map on the left is essentially the market for off-grid wind turbine capacity. The market for off-grid wind systems in Nepal. So you'll see that many areas of this map of Nepal are blank. That is not because there is no wind resource. It's not because there is no potential market there. That is because we considered in our analysis that these areas that have been covered in blank here either have too small a population to support and be supported by a wind system, or it is too close to the current electrical infrastructure system, i.e. the national grid. On the right, you can see the model geographically varying costs for maintenance visits per year. So you'll see the cheapest areas for maintenance costs are in the center of the country and in the southeast of the country. And that is purely by virtue of being closer to the maintenance hubs where technicians are trained and are deployed from. So that's a function of the proximity, but it's primarily a function of the travel time. Places in blue in this map are quite close to the maintenance hubs, not purely in terms of straight line distance, but in terms of how long it takes to travel from one place to another. So you'll see in the northwest of the country, this is the high mountain region, quite inaccessible. This is the most expensive in terms of maintenance costs, as it is not only further away from maintenance hubs, it also takes longer to get there. So having gone through quite a rapid pace, I think, a history of some of wind empowerment's market assessments, I should talk about the different stages of the methodology. So the first stage of the methodology, as Kimon mentioned, is to learn from existing initiatives. It's no good to go into a new context or even an old context and not learn the lessons from the past. Almost everywhere in the world has had some attempts at implementation of small-scale wind turbines. So from understanding how these fared and why, we can begin to understand what the critical success factors for small wind are. Is there a chronic issue of poor maintenance in the country? You know, is certain regions of the country subject to unfavorable environmental circumstances, and so on. The key output from stage one is the identification of scalable delivery models, and this is something that the delivery models group will talk about just after our session. But also the critical success factors, what makes small wind in this context successful or not, as the case may be. So stage one is performed through site visits, through discussions with people who have already implemented small wind turbine projects, and through expert interviews, just to be able to understand what the landscape is and what the context really means for small wind turbine projects. Stage two is quantifying the potential market. The key output from this being the market size and location. So as the maps I showed you previously, that shows the distribution of the market size. So you can then start to divide that up and say, within this area, there are so many kilowatts of wind turbines recommended as part of the optimal system. So this is done through different forms of geospatial and techno-economic modeling. More recently, the Nepal market assessment used a combination of HOMA and GIS software to model the optimal system in each location based on wind resource, solar resource, geographically varying diesel cost, geographically varying maintenance costs. So what we did was we allowed HOMA to design the cost optimal system for each location, depending on that location's demand, solar resource, wind resource, and so on. And then it produces for each location on the map I showed you, the optimal system. We can take from that optimal system design the ideal capacity of small wind turbines. Once we've got that, stage 3, mapping the energy access ecosystem. So this is where we start to draw out recommendations and conclusions and start to think about the whole enabling environment. So we think about what the key barriers to small wind scaling are, what needs to be addressed in policy, in regulation, in technical capacity, and so on. And then start to put forward actual actionable recommendations, you know, things that really not only posing the question, but providing something of the answer. To be able to take that forward and hopefully make small wind more of an optimal solution. So the key output for stage 3 is recommendations for targeted interventions. And I think the word targeted there is quite important because you can make hundreds of recommendations, you know, but if they're not targeted, if they're not specific, if they're not relevant, then it's again a waste of resources. You want to think about which aspects are really key, address those, and then address the smaller, you know, more detailed obstacles. So it's about resource and time prioritization more than anything. So I've spoken in some detail about these steps already. I've just got some nice images. This is another photo from one of the site visits. Conducted it as part of the Nepal market assessment. And then this is a slightly more complicated, possibly less nice image of the process that is involved in the techno-economic modeling stage of the assessment. So this is used for quantifying the market. I'm not going to spend too long displaying this screen, and I appreciate it's got quite a lot of detail on it. This is available as part of a paper which I will share in the chat just after I'm done speaking. But the inputs to the techno-economic modeling are here. We consider the renewable energy resources, we consider the diesel price, the accessibility maps, how long it takes to travel from, for example, a maintenance hub to a rural community, the component costs, how much does an inverter cost in the country, how much do batteries cost in the country, and then representative demand profiles for different communities. We then feed this into a techno-economic modeling process. I've been using the HOMA microgrids tool. You don't have to, there are other tools available. It fits, other tools would fit equally well within this process. All we need is, from this initial process, is outputs. The outputs being the optimal systems for each load profile and each different combination of inputs. And then that also gives us the spatial variation of costs for each system. We feed that through a second filter, which includes the ability to pay of the communities, the existing access to electricity of the communities, the population density, and any unsuitable areas. So by removing places where we know that the system cost is too expensive for the community, we remove areas that already have access to electricity. We remove areas that are insufficiently populated. People don't live there, basically. And we then remove areas that are unsuitable, for example, protected areas, or areas that would otherwise be unsuited to small wind installation. By removing these areas, we can then calculate what the market size is and look at what the realistic geographical distribution of optimal system types is. This is an image shamelessly stolen off John Leary. I hope he's still there. But I think this is a fantastic image. This just shows the breadth of the enabling environment that we've been talking about. Like I say, it's not just about the market. It's not just about investors. It's not just about how much money is available in an area for small wind. We need to think about the manufacturers, the transport. We need to think about any neighboring installations. We need to think about where the grid is, how universities can factor into this, how community technicians can be involved. Is there a demand for training centers? Is this something that could scale up in many different areas or just one particular region, and so on? And through expert interviews, actually talking with all of these different stakeholders, and through literature reviews of what has worked and what hasn't worked in the past, from the perspectives of these different stakeholders, we can then start to draw out these recommendations. And I think one of the key points of the Nepal market assessment certainly is that the recommendations we have made are specific for different groups of stakeholders. And that's important because you can make blanket recommendations that aren't specific to any particular group of stakeholders, and then nobody will do anything because they don't realize that the responsibility is on them. So I think that's a very important part of things as well. I mentioned a paper that I will share later. So this is a recently published paper. I think it's open source. I will share the link in the chat. But this goes into a little bit more detail, a little bit more into the technical detail, certainly, of everything I've just discussed. So this reviews different market assessment methodologies and then presents the wind empowerment market assessment methodology as I've been discussing. So I will share that in the chat in a second. So thank you very much. I mean, it says questions here. I will ask you to save your questions for the discussion session afterwards. Hopefully you've enjoyed that. And I think I will then pass on to our next presenters. Thank you. So Luis, I think it's your turn next. I will stop sharing my screen if I work out how to do so. There we go, that's easy enough. Thank you. Luis, take it away.
Thank you, Alfie. So, hello, everyone. And first of all, I must say that even though I've been following the activity of wind empowerment for years, I could say that this is my first contact with you. So I'm happy to be here, and I thank you for the opportunity to share some of the information related with this project, which has a strange name, WEOnline2020, that I will be sharing with you during these minutes. As probably I'm one of the newcomers here, please let me introduce briefly myself. I work in Spain, in CIEMAT, in Madrid. Marco was asking about that. Yes, I'm based in Madrid. My background is electronic engineer, and my main expertise, I would say, it's systems related with renewable energies. I started working with solar photovoltaics, but since 1998, I've been involved also in small wind turbines. And mainly in these areas, but also in other ones like testing, sizing, assessment, specification, and so on. So the strange name of this project, this WEOnline2020, stands for Small Wind Turbine Optimization and Market Promotion. And the main objective of the project is precisely that one, the promotion, development, and implementation of the utilization of small and medium-sized wind turbines. The project was supposed to last for 3 years, ending in 2019, but it has been extended till the end of 2020. So we are finishing the project right now. Well, really, we are finishing some of the partners because this is a strange project, which is an net lag model type of project, which is particular because each partner gets funding from their national research funding agencies. So each partner has a different funding source and a different time schedule. So, for example, some of the partners have already finished the project 6 months ago, and some of the partners we are still working on the project. The overall budget of the project was more than 1 million euros, of which more than 600,000 euros were funding. We are 8 partners in the project. 4 of them are from Europe, and 4 of them are from South America. CEMAT is the coordinator of the project, and the partners from South America come from Mexico, which is INEL, INTEC from the Dominican Republic, INTI from Argentina, and the University of the Republic from Uruguay. The other 3 partners from Europe are ISTEC from Turkey, UTCN from Romania, and VTT from Finland. The structure of the project was composed of 5 working packages. The first one, or the 01, is the project management. And the main 4 working packages are the first one is the promotion of the market, the small wind turbine market. Second one is the wind resource for small wind turbines. The third one has to deal with the optimization of wind turbines. And the last one is related with the standards for small wind turbine. As the session in which this presentation has been included is related to the market, I think I will talk in a bit more detail about this working package related with the promotion of the small wind turbine market. And the rest of the others will be covered more in less detail. Starting with the project management working package, one of the main outputs of this working package has been the creation of a web, which of course you are invited to visit, and some reports of which the final report will be also available, publicly available on the website. In relation to the promotion of the potential market working package, it was included 3 tasks. First one, the analysis of the market. The second one, the realization of workshops. And the third one, the preparation of material for education. As I said, I will talk about each one of these tasks now, starting with the analysis of the market. There were 2 deliverables associated with this task. The first one, the sample survey form. This deliverable, this report, was to study the existing survey forms from previous analysis, like the ones that have been presented before. And in fact, you can see it's over there in the list. But in this work, we identify 5 different scopes for the performing surveys related with the small wind turbines. The first scope, maybe it's the more common, which is the market deployment assessment. And for this, we presented the survey form from the IEA task 27. The second scope we identified was your scope, with the wind empowerment market assessment methodology that has been presented right now, which also included a survey form. When we talk about survey forms, we are talking about the templates in order to perform the surveys. The third scope is related with the practical aspects. For this, we found a reference in the Austrian market experience. The fourth scope is the social aspects of small wind turbines. And here we found two templates or two survey forms, one from the SWIP project and another one from the UK survey. And the last scope is has to do with the regulatory issues. And for this scope, we found a reference on the survey carried out for some communities in the US. All of these survey forms are in the report. We also, within the SWOTON project, proposed our own survey form. And in fact, it was not only one survey form, because there were different countries involved, which had already, some of them, performed some surveys. And so we found several sample survey forms. In particular, one from Argentina, from the INTI, one from Mexico, from INEL, and the one that we from CEMAT developed for this project. Second deliverable for this task is the results. Once we know about the forms, those forms are used for surveys, and this report shows the results of those surveys. Starting with the existing surveys, this perhaps has been one of the most common deployment market analysis for small wind turbines. The results shown in the studies from the World Wind Energy Association, which covered till 2014. From that time on, those reports from the WWEA were not any longer available. And then this information was available in the reports from the Department of Energy in the US. In particular, they shared the statistics of the market, of the, we could say, main markets, the main countries where the small wind turbines were active. And well, if we take a look, there was a question from Greece, if there is a market for small wind turbines. Well, his question was on the developing countries, but he made the same question this week on another conference for the developed countries. If we take a look at these figures, it looks like, if we look at the global figures, that the market more or less is steady. But they are somehow cheating, because really there is no stability. What happened during those years is that some markets in some countries were decreasing, and at the same time, some markets in other countries were increasing, and the total seemed to look more or less constant. There was not such an stability. In fact, the results for 2018 which are not here on this table, but show an important reduction in the total figure, around 50% of, around, we could say, 50 megawatt total. This is something for sure familiar for you, because it's stolen. Stolen because it's the reference, but it has been taken from your reports. I think it was from the global market assessment carried out by Green Empowerment. And we were in this figure, the two countries participating in this SWOTON project, Argentina and Mexico, that appear on this table, on this graph, are particularly signed, especially Argentina, which is in this analysis one of the countries where the market seems to be more favorable. In fact, well, it's not here, but it is in the report. It is also shown during this global market assessment, Argentina was taken as a case study. And the results for this case study of Argentina are also shown. So those were the results of previous surveys, but we, within the WEOnline project, carried out our own surveys within our countries. And well, the results are different depending on the countries, and also different depending on the level of detail. In particular, some countries have carried out a more detailed analysis, more detailed survey, like Mexico, Argentina, Spain, or more or less Finland. Here's, for example, a result from the Argentina study. This survey was carried out some years ago, and it was carried out when the small wind industry in Argentina was very active. Nowadays, it's not so active, but at that time there were several companies working on the sector. This is a figure from the survey in Mexico, which is showing the number of wind turbines, small wind turbines installed each year during this period. And this is a map taken from the survey in Spain, which in this case is showing the geographical distribution of the deployment of small wind turbines in Spain. There are two other countries which are included in this analysis, which are the Dominican Republic and Uruguay. But in this case, in these cases, the deployment of small wind turbines has been very low, and there are hardly any implementation of the small wind turbine, particularly in Uruguay. The Dominican Republic, there are some small wind turbines installed, but there were no official survey. So in this case, the partner from the WEOnline project took the information from the imports of the small wind turbines, and with that information, we established a possible result. The second task within the promotional potential market working package is the elaboration of workshops. In this sense, we have been quite active, and we have performed 4 workshops. One of them, the first one in Mexico, in Huatulco. 2 of them were associated with Arribas. Arribas is a network which is for South American and Spain and Portugal related, also with the small wind turbines, but in particular for distributed applications, grid-connected applications in urban environments, which maybe it's also interesting for some of you. In these links, you can access the presentations of each one of these workshops. And the third task within this working package is the preparation of material for education. This is one aim that from the beginning we were interested in, as all of the partners involved in this project are either research centers or universities, and we thought that it would be fine to make an update, to produce an updated material for education. After several discussions, we ended up producing a new educational material. Unfortunately, at the moment, it's only in Spanish, and it includes these 10 chapters with also an introduction, which are somehow related to the activity carried out during the project. But this information is being published right now. It's not yet publicly available, but it will be shortly. And the idea is mainly that in this case, anyone can find some updated information, in this case in Spanish. Okay, so that was for the first working package, which is the one related with the market. Now we move quicker to the second working package, which is related with the wind resource. It included also two tasks. The first one has the aim of comparing the results of applying the commercial tools like WASP or WindPro for small wind turbines and validate those results with real world measurements. In particular, it was validated in one site in Soria in Spain and with other sites in Turkey. The results are that in general, the conclusions are that in general, the results of this validation are good whenever there are not many obstacles around the small wind turbine. If there are obstacles around the small wind turbine, the results coming from the commercially available tools usually are not precise enough, accurate enough. The second task included the development of a methodology for the easy assessment of local resources with available and free information. In this sense, the Turkish partner developed a web page which included a tool to perform this easy assessment. Unfortunately, the web page was supposed to be publicly available, but at the moment it is not, because the partner has run out of budget and now is looking for some other funding in order to make this web publicly available. The third working package, you remember, it was related with optimization and included 4 tasks, of which the fourth one has been removed because it has not been carried out. And even the other one, mainly the third one, has not been carried out as it was originally proposed because of some limitations within the project. The selection of the small wind turbines was carried out, and 2 wind turbines were selected. I will describe now. The first one was this small wind turbine from Argentina, the Local wind turbine. By the way, Local is, I don't know if it's a partner directly of Women Empowerment, but of course it's a friend. I know that the director of Local is a friend of Women Empowerment. It's based on the Cupico design, and they produced some models, but in particular the 1 kilowatt model, they were interested in connecting it to the grid. So they had a battery charging model, but they wanted to produce a grid type model. For this purpose, they developed a high voltage generator, and in order to use an existing PV inverter to connect it to the grid. As the input voltage range for the PV inverter is between 60 and 450 volts, the output voltage of the generator should be in this range, which is not common in small wind turbines. That's why the new generator was built. But even though the generator output was in the range of the input voltage of the PV inverter, some other power conditioning was needed, in particular to control the damp load, and if so, to perform the MPPT for the wind turbine. This manufacturer contacted with the project, and so the project took this interest as a particular design improvement for this task. You can see on the right, on the bottom, this is also scheme that may be familiar for some of you because it's also taken from some documentation from Wind Empowerment. But this was a scheme open source for the design of a load controller for low voltage and also for battery charging. As we were dealing with a high voltage generator for grid connection application, some changes were made, but afterwards Argentinian University has also been involved in the project, and they are developing, say, much more complex converter, performing also the MPPT for the wind turbine. The other case study that was selected for the project was from Mexico, and from this manufacturer, which is Aerolud. They also were interested in connecting the wind turbine to the grid, but in this case, using what we could say a commercial wind inverter.
Hi, Luis. Sorry to interrupt. Could I just ask you to take the next 5 minutes to wrap up in the interest of time?
Yeah, sure.
Okay, thank you.
Yeah, sure. Okay. Well, in fact, we were nearly getting to the end. So,
perfect.
Thank you. And so for this purpose, a new generator was designed, which is patent pending. But the problem with this case study is the manufacturer Aerolud ceased its activity with wind turbines during the project, and so it was Enel, the partner involved in the project, that took the activity, but only as a research activity. There was no longer a manufacturer involved. So this is the last working package, which is related with the standards. And in this sense, I would say that it is following up this activity mainly under the task 41 from the IEA. And that was all from my side. Thank you again. And of course, I will be glad to comment on any questions you may have.
Thank you so much, Luis. That was great. And I'm sure there are questions already in the chat, which we will come to shortly after we've heard from Jose Armando. Jose, are you there?
Hello, Alfie. Hello, all. Do you hear me?
Yeah, we can hear you fine. Please begin your presentation.
Yeah, I will share my screen. Please let me know if you can watch.
Yeah, we can see that. Perfect.
Perfect. So, well, good morning from Peru. I don't know what time is in your country, but first, let me introduce. I'm Jose Armando Gastelo from Peru. I am mechanical electrical engineer. I studied in Peru in the Pedro Ruzgay National University and at the National Polytechnic Institute of Mexico. I worked on renewable energy since 2017, and I have participated in several conferences around the world in US, UK, India, and United Arab Emirates, and other countries. And currently, I develop renewable energy projects in Peru and for Latin America in a international company called NG. And besides, I am part of the United Nations work group of the Sustainable Development Goal number 7. I co-founder too of Microgrid for Sustainability, which is an organization which seeks to promote energy access and energy transition using renewable energy microgrids. Well, today I want to tell you about microgrids for rural electrification. We, inside my organization, and together with some member of Wind Empowerment, we were working in the use of microgrids that it's a system which join photovoltaic, wind, and other renewable energy systems to provide electrification, access to energy in rural communities. So my presentation of today will be focused on my country, on Peru. First, I want to start with a presentation about the energy access in Peru. What is the situation now? So now Peru still has problems access to energy. Peru in the last decades has developed a great growth, economical growth, social growth, but it still has problems related to access to energy, especially in rural and remote areas. Okay, so this is Peru, it's in South America. Um, and there is currently there are like 1.5 million of inhabitants in my country without access to electricity. So this is a problem now because it's a goal to reach to 100% of electrification in 2030. So, and besides, there is around 50% of electricity generation using fossil fuels around in the whole country. So we have like country, we have to overcome the electrification rate and to overcome the great percentage of generation of electricity using fossil fuels. We have to make an energy transition because 50% is using fossil fuels and the other 50% using hydroelectric, big hydroelectrical. So we have to include the not conventional renewable resources. And the common electrification in my country, in Peru, it's the conventional grid extension. So we have to, all electrification project consisted in a grid extension to reach to all places. But this is difficult in a country with the Andes at the middle of the country and with complex geographic. Okay, so we call this the Amazonia problem. Peru currently electrify the whole country using an interconnected system, which is called SEIN. SEIN means a national interconnected system. And this interconnected system is the system that you can see here in the left figure. The red, the green, the blue, and the orange lines are the interconnected system, the SEIN. And this system are transmission lines of high voltage. And as you can see, in the coast of the country, this is the sea in the coast of the country, there are almost all the coast of the country has access to the interconnected system, and due to that has access to electricity. In the Andes is like the same, but in the Amazonia of the country that this is near to Brazil, we have the problem that there is no interconnected system because the geographic is really complex for transmission line to reach to these places. Okay, so here the dot line, okay, the dot line is a projection for a new transmission line that I will told you about it later. But as you can see, the Amazonia problem has a great the Amazonia has a great problem here. And one of the best examples to illustrate this problem is Iquitos. Okay, Iquitos is the capital of Loreto. Loreto is the greater region of the Amazonia of Peru. Is this state, this department that is inside the score. And Iquitos has around 500,000 people only in Iquitos. And in total, there are around 3 million people without interconnection to the system. This is around the 10% of the complete population. So we have 3 million people without interconnection. Some of them has access to electricity, but using thermal plants or using small photovoltaic systems that one cause pollutions and the other don't provide productive uses. Okay, don't provide access to quality energy, only some hours, only the capacity to light a bulb, to charge a cell phone, and nothing more. But Iquitos is a good example to illustrate this, because this is assumed to Iquitos. And as you can see, there are several rural communities near to the capital, and only the capital there are around 500,000 people. There's a lot of people, because you know that here in Latin America we have a lot of people, more than Europe. But this is like a complete country in some European countries. So there are a lot of people, and there is a lot of demand too, because here only in Iquitos, the demand of electricity is around 50 megawatts. Okay, there is a medium voltage line, but all of the generation plants in Iquitos are thermal plants. Okay, and there is a medium voltage line of around 130 kilometers, and with these characteristics, Iquitos is one of the largest of grid systems in the world. And this is a problem. Why? Because all of electricity that is consumed and that is provided to this population, that is a great quantity of electricity, is generated using thermal plants. Okay, so we have a critical problem in our country to solve this problem of the Amazonia problem that has Peru. Peru, until now, it's not possible to solve this problem, because the unique solution, the unique view that the country has is an extension of the grid. Okay, and with an extension of the grid, it's really expensive to reach to these places. Okay, so what is the current solution by the government now? Well, as I told you, it's a new extension of the transmission line. Okay, this transmission line that you can see in the here. Wait, yeah, here. This is the new transmission line that the government have planned to install or to implement, and it's called the transmission line Moyobamba-Iquitos. Okay, Moyobamba-Iquitos, it's a new transmission line this project is since 2011, and the government has the plan to install around 600 kilometers of this transmission line from the city of Moyobamba, that is near to the Andes. It's between the Amazonia and the Andes, until Iquitos to interconnect Iquitos to the sea. But what is the problem with this project? First, that it's really, really expensive. The investment, it's around $500 million. But the government will pay $2,200 million, $2 billion, more than $2 billion during 30 years of the project, because, well, a private company go and invest, but then the government have to return this investment, and the investment is around $500 million, but the government will pay around the country around $2,200 million. And this is a lot of money to electrify Iquitos, because yes, the demand is high, but it's not so high to make profitable these. Okay, but until now the problem wasn't the economy, because as you see, the investment and the profits are really good. If you invest $500 million and you will obtain $2,200 million, there are a lot of companies that want to invest in Peru in this project, but currently suspended due to environmental and social problems. First, the environmental is that this new transmission line will through 600 kilometers of old growth forest, of virgin forest. Okay? And this will impact in several biosystems, in several ecosystems. And well, there is a lot of problems now with some international organization of environment, right? The second problem, the most important, is the social problem. Here, there are a lot of rural communities, a lot of native communities, thousands of them, and these people don't want this project or this transmission line um, will be constructed in their places. So currently suspended, and it's the most probably that this project never could implement in our country. So the problem of the Amazonia continues because we don't have solution. And as our organization, we want to provide another point of view using renewable energy microgrids. So we say, well, instead of electrifying these rural areas through grid extension, and that is not economically viable and causes an environmental impact and social impact too, we, excuse me, wait me. Sorry. Well, instead of electrifying these rural areas through grid extension, or by using a small photovoltaic system that don't provide quality energy, we intend to implement renewable energy microgrids. Okay, to replace this project using renewable energy microgrids and allowing economic development. Okay, this type of microgrids provide quality energy and allowing economic development. So this was our first project. Wasn't in the Amazonia of Peru, but was our first pilot in Peru, and was installed in Laguna Grande together with the company called White Energia. And the funding was by the IDB, by the Inter-American Development Bank, and through a contest called Ideas. Okay, this contest was a contest to provide funding to interested and clean projects. Okay, so we participated in this contest, and then together with White Energia, we installed. Well, to be honest, the complete work was done by White Energia, but White Energia installed this microgrid in Laguna Grande. Okay, you can see here is at the middle of the country in the coast. It's a fishing community, and here is you can see here the picture of the community. Okay, and this is the microgrid we installed in that community. Okay, we installed a microgrid composed by wind turbines, by photovoltaic system, and using a battery bank and inverters and controllers to provide around 12 kilowatts of power. I think that was 6 kilowatts of wind turbines, 2 of 3 kilowatts each one, and 6 kilowatts of photovoltaic. Okay, so we have here 12 kilowatts of power and a capacity of a battery bank of around 800 ampere hour at 48 volts. So this was our first pilot in Peru, and then we say, well, we will study if we implement this type of microgrids, but in the Amazonia, in the rural communities of the Amazonia of Peru, to solve the previous problem I told. Okay, and this was the cases of study that we made in the last months. And the object of this project was to study the profitability of microgrids for electrification of rural communities in the Amazon of Peru. And we follow the next methodology. First, we use geospatial data analysis of around 2,000 rural communities. And then we made an estimation of electricity demand using this data. The data consisted in number of households, that was the population, solar radiation, wind speed, and distance to the grid. So with the number of households, we made an electricity demand estimation. Why? Because we want to know what is the demand, because as Alfie told, the market assessment doesn't consist only in resources or only in resource evaluation. Include to the demand, because if there is no demand, well, there's no potential for that. So we studied the electricity demand estimation in that rural community, and then we made a cluster of the electricity demand. We group these 2,000 rural communities into only 12 clusters. Why? Because we made a design of microgrid for each cluster. If we wouldn't make this cluster, we would have to design around 2,000 microgrids, and that is a lot of time. So we made this cluster to design only 12 microgrids, and then we made the design of the microgrids. We obtained the LCOE, and finally we calculated profitability, and we rendered these results using GIS program, okay, a georeference information system program. Here at the right of the slide, you can see the diagram flow that we use in the project. Okay, first we start with the data, and then we made an evaluation with minimum requirements. Okay, there we define a minimum require of households, because this is related with the electricity demand, a minimum require of solar radiation, and a minimum requirement of wind speed. If the rural community match or accomplish with at least one of these accomplished with at least one of these requirements, we continue with the electricity demand estimation. But if not, well, we decide that there is no potential in the rural community. Then we made the electricity demand estimation, followed by clustering of the electricity demand, design microgrids, calculate the capex, the capital expenditures, and the operational expenditures, and at the end we calculate the LCOE, and we define if this LCOE it's higher or is lower than the current price of electricity in Iquitos that was using diesel. Okay, so if there is higher, this means that there is no potential. If it's lower, so we obtain that yes, there is potential, and we end the algorithm. Okay, so here we have our main results. Okay, so a total 2,000 population center were analyzed, and this all were grouped in 12 clusters based on the energy demand. Okay, so we have the 12 clusters, okay, that we obtain from the 2,000 population centers. As you can see, it's observed that the electricity demand of the communities most frequently is between 30, that is this is logarithmic scale, but 30 to 100 kilowatt per day. This is the most frequently consumption of the communities. The other important result, and this is really related with wind, is that an average wind speed of 1.2 to 10 meters was found for almost all rural communities, and due to this very low potential, because this is almost that there is no wind potential. Wind power systems were not considered during the micro design process, and this is something bad because at the beginning we want to consider wind turbines in the microgrid, but at the end we have to say that there's not possible, because at least in the Amazonia, maybe in other places of the country, yes, but at least in the Amazonia of Peru, there's no potential for wind. So at the end, we made this type of microgrid to make the market assessment. We include a photovoltaic system, an energy storage system, and these systems were coupled using a DC bus. Then we have an inverter, and all rural communities has a medium voltage grid and a low voltage grid. Okay, and medium voltage grid because the distance to other communities are far. Okay, so we have to transmit in medium voltage to reduce the loss of energy. At the end, we designed 12 possible microgrids with different technical and economic characteristics. Well, here at the right, you have the result using the GIS that show the LCOE of rural communities for the for the communities we studied. All right, we have typically the results that you have in green are lower results than diesel, and the result that you have in red, it's higher. As you can see, the most of the communities has lower values, so we obtain that this is good, and this is a meaning of profitability of these types of communities, of this type of microgrids for rural communities, at least at the Amazonia of Peru. The most frequency value was between 158 to 186 dollars per megawatt hour, and this is lower than the LCOE current rural electrification project in the Amazon, which include a small photovoltaic system and thermal plants. And this work was presented some days ago in the Smart Grids and Energy Systems International Conference that was held virtually in Australia. And this is the title of the work that we presented. Alfie was one of the authors of this paper. So in some days will be published and indexed in Scopus, so I will share with you. Well, the future work related with this project, with type of microgrids promotion that we want to do. It's first that we have to include wind turbines locally constructed, maybe not for Amazonia because there is no potential there, at least at the most of communities, but in places like our project that we made in Paracas, in Laguna Grande. Yes, these are commercial turbines from a Chinese provider, but we have to include locally constructed wind turbines. Finally, other future work is improve the analysis, because we have to consider better information for various sources, for several sources, because the current data provided by the government has some issues that need to verify. Our next work is to analyze the profitability to replace the Moyovan-Bequitos transmission line by several microgrids to electrify the Peruvian Amazonia, because now in this work we compare against thermal and against photovoltaic systems, but our next step is to compare against the transmission line project. And finally, we want to implement a microgrid in the Amazonia, like our first microgrid in the Amazonia of Peru. And currently we are working in the development of project to implement a renewable energy microgrid in the Amazon to obtain real results of operation. And we are under search of funding now for that. In conclusion of this presentation, there is a high potential for implementation of hybrid solar energy storage microgrid in the Peruvian Amazon, especially in many dispersed rural communities near to Quitos and in communities next to rivers. The LCOE values obtained for the microgrids is lower than the LCOE of current thermal plants, small photovoltaic systems. Microgrids provide reliable electricity and do not emit polluting gases, while thermal plants are polluting, and a small PV system provides neither reliable nor round-the-clock electricity. We need to include wind turbines locally constructed, and we need to install more microgrids to compare our study and to promote the use of renewable energy microgrids. But that's all. Thank you. You can contact with me with my WhatsApp or with my email or by LinkedIn. And there is a question I think that we have to answer at the question session, right?
That's right. Yeah. Thanks very much, Jose. That was fantastic. And just keeping time in mind, I was hoping that we'd finish slightly before 1/2 the hour, so we can have a break just before the delivery model session. But before we can think about having that break, we've got a lot of interesting questions to answer. So I think the first thing that we should start talking about is, well, I mean, before I get onto that, I guess I will open the floor for people to come in with questions on the presentations we've just heard. I'm trying to work out how we can unmute everybody now. Oh. Do you know how to do this, Kimon? Because I don't.
Yeah, I'm also looking for it. Alfie, let me see.
I think it's okay now.
No, I mean, Adrian, I invited you specifically. I'm not sure how to invite everybody to talk. Anyway, well, Kimon, can you figure out how to do that? And I'll start talking about the questions we've got. Luis made the point, he asked in the questions, is there a market for small wind in developed countries?
Alfie, you are mute.
Okay, I'm back now. Apparently Kimon muted me, but that's fine. That's fine.
It wasn't intentional, Alfie. Just
No, it's okay. So Luis, I'm not sure how much you caught of that question, but Luis was asking about the market for small wind in developed countries. He said no at the 4th International Wind Conference this week, and it was a heck of a ride. It's a difficult question to answer. It's a difficult question to ask. At scale, in developed countries, you know, it's going to be difficult to advocate for small wind at scale in developed countries, especially where the grid connection is near 100%. There's going to be only very small communities that don't have electrification access already, and a very, very small proportion of those that are best supported by small wind turbines. You know, so is there a market? Yes. Is it big? Probably not. It's not something I've been working on looking at specifically. So I'm sure there is a market. Is it of any appreciable size? I'm not so certain of that. Other people may have different views. So we had a question from Emmanuel from Ernie Wind Turbine Collective asking which company were the 10 kilowatt wind turbines in the off-grid systems in Nepal, where the battery system were damaged after 1 year. I think the answer to that is, I don't know. I don't think Kimon knows either. If we've recorded that information, it will be in the report that we've shared in the chat. And Luis asked about the market assessments. At this level of complexity, does the market assessment become a social assessment? The answer to that is, well, yes. It's not just a social assessment either. In fact, in part of my own work, I've been trying to steer away from using the term market assessment, despite the name of the working group and despite the name of the session. Because as I've said previously, you know, you say market assessment and people have, you know, ideas already in their head about what a market assessment is. And it is social, it is technical, it is all of the above. It's by no means just focusing on the market, or it is, but the market isn't just an economical thing. So I've answered my questions, and I'd like to open it up to Jose and Luis to address any of the comments that they've seen.
Yeah, sorry. I think that you told me that some minutes ago I was out because I needed to ask some call, but I'm not sure if I have a question to answer.
So Marco has asked, in the Amazon case study, why should you consider locally constructed wind turbines when you know that you have a wind speed at 1.2 meters per second at 10 meters height?
Yeah. Well, in that case, I refer that we have to consider locally constructed wind turbines for another places, like for example, okay, the microgrid that we installed in Paracas, that is in the coast of the Peru, that I show previously. In that case, we install with commercial turbines. So I think that we have to consider locally constructed in that cases. I think that for Amazonia not, because at least there is no potential. Maybe it could be for education or for something or other purposes. But yes, in summary, we will consider locally constructed for other places.
Oh, we have somebody with their hand up. We have Jorge with his hand up. I will invite you in to talk, Jorge, please. Go ahead.
Yeah, I wanted to comment. Can you hear me?
Yeah, we can hear you.
Okay. I just wanted to comment regarding this value of 1.2 meter per second in the Amazon. At least from my experience in Oroville, which is a very wooded area, because we are so close to the dense forest, the wind speed increases as you go up above the trees quite fast. So 10 meter per second is basically, we never install anything at 10 meter per second in Oroville because the treetops are 15 meters. So I don't know if that would affect the same issue in the Amazon where you're basically in a very dense forest. So you really have to look at probably turbines at 30 meters or above. So, and probably at 30 meters, you would definitely get a much better resource than at 10.
Yeah, that is probably because we consider only, well, we can only measure at 10 meters of height, but maybe obviously that higher could be better resource. And I think that we want to include that. We will include that in our next words. Thank you for that recommendation.
Sure. And Luis has also asked in the Q&A function, what is the role of empowerment in these microgrids? Isn't education a key factor as well? Wouldn't approach about education to be considered when designing the microgrid that would not justify wind where there is none, but it would justify building something together or integrating the education scope to the microgrid? This is hardly possible with anything outside of the Piggott design. Luis, maybe this is a bad decision given that we have 5 minutes left in the session, but would you like to elaborate on that?
Okay.
Sure, I can elaborate. My question is, I've seen you guys are doing very interesting market assessments, and you're looking into the resource, you're looking into some of the logistics. But what about this capacity building potential of locally manufactured technology, or at least locally assembled technology? How do you equate that into your market assessment? How does the impact, the social impact, can be measured or estimated through market assessment? And maybe, just maybe, it would justify building a wind turbine somewhere, even if it's deployed somewhere else across Peru, build it in the Amazon and take it somewhere else. I don't know, maybe it's crazy, but the idea here is that, empower people. And even if they don't use the turbine in the end, someone else will, and that kind of creates something. Yeah.
Yeah, well,
sorry, go ahead, Jose. I was going to say I could answer, but I'll let other people answer because I talk too much. So go ahead, sorry.
No, thank you. Well, first, in my case, we didn't consider the locally constructed wind empowerment yet. We will consider in our next words. But yes, for example, here in Peru, there is a government project to implement small photovoltaic systems, but never is considered this part of improvement or engagement of the community, the people of the community. And at the end, the project of the small photovoltaic system finished in bad condition, finished not working, and it's an investment that don't have utility at the end. Okay, but yes, I think that it's important to include this education, this engagement, this previous formation of people before to install the system. And I think that in Peru, in several countries of Latin America, is not considered, but we have to consider that we will have.
I can't hear. Shut up.
Andrew, I'm not sure if you realize that your microphone is on there.
How unfortunate. Excuse me. I did actually want to ask a question, but sorry if I just interrupted. I'll mute myself. But
No, please go ahead if you're going to ask a question. I think Jose was done. Yeah.
Apologies for the noise interruption. No, it's a question kind of following on from Luis's statement, actually, about whether there's a template for post-training market evaluation. So once you equip people to create locally small wind turbines with local materials and local workers, what kind of a market assessment can you do measuring the impact after that? I'm just wondering if there are templates of that nature.
So I'll quickly take that. That's a
and I'll
good...
go on mute, sorry.
That's a very good question. And I think the answer to that is, you know, at that point, is it a market assessment anymore, or is that touching on the realm of delivery models? Is that what, you know, you've conducted an implementation, you've implemented the system, you've already had a market assessment. After you've started to enact things, you're delivering. So that's where the boundary between market assessments and delivery models starts to blur. And I think there is a need for that kind of assessment. Is it a market assessment? I'm not sure. I think there's a definite role in what we do to take a look at that for sure. But I think this is something that we can discuss in the next session, in the delivery model session.
Alfie.
Luis?
I just want to chip in one very quick thing on this to answer to Andrew's questions, that Wind Empowerment is currently writing a book on small wind-based microgrids or systems. So you're more than welcome to join, Andrew, because we're also recruiting people to contribute to different sections of the book. And we have a pre-project, during the project and post-project sessions and sections in the book. And we have a special chapter dedicated to assessing the impact of the installation, which means it includes the delivery model impact and, you know, and the impact in general. So Wind Empowerment is actually working on this right now at this moment. We're trying to get together to work on this.
Fantastic. Thank you. No, I'll look for that on the emails.
I think I can add a little bit to that discussion about educating and training thing and how important it is from the question of Luis. One of my own project experience on constructing a locally fabricated small wind turbine and installing it in a remote area. We found out that sometimes we forget that in a very remote rural location, training and educating becomes a bit difficult because people do not have enough technical background, and it's a bit difficult to think about going to the community group and giving enough educating or training things that they would pick up. It's not a matter of just doing one workshop or two workshops. It has to continue over a long span of time so that we can ensure that they would be able to maintain such systems. But something that we tried to do with one project was that the off-grid location, the community where we were trying to electrify with the locally fabricated solar wind and solar system. There was a city, not a city, small town actually, a few kilometers away from the off-grid location, where we tried to find out small repairing hubs or similar metal workshops, or even like house wiring workshop or house wiring places where giving training to those small companies made much sense, which would kind of like be able to do those repairs which is needed in a year or 2 years period. So it's a bit difficult and needs a bit more thinking about when we talk about like very remote off-grid electrification scenario.
So I realize that many of us could talk about this subject for quite a long time, me not the least. I could go for hours, but we have overrun slightly, and I did want to allow people a short break before the next session. So if there's a pressing question from anyone else, I will take it quickly, but just the one question. And if not, I will draw the session to a close, and thank you all very much. One more question. Anyone want it?
If nobody has question, I'd like to jump
Go
in.
ahead, Kimon. I guess you
I think there was some question from our attendees, which would definitely get more priority.
Sure. I mean, on the question of questions, you know, I think all of us are available by email. Certainly, we can discuss further on Discord or somewhere else. We can be contacted through the Wind Empowerment website, for example. And the recording of this session will, of course, be made available online, if that helps to spur any thoughts.
Yeah, quickly getting to my question. My question is to Jose. You were mentioning about levelized cost of energy, and my question is, your assessment said that levelized cost of energy is attractive in some cases, but I'm curious to what length of system operational period is considered, and whether it also considers cost of long-term replacement like batteries and inverters, which generally comes to quite expensive in most cases. The cost of energy becomes quite expensive. I was wondering whether you'd consider those costs as well.
Yeah, it's not very expensive, but yes, it's a little expensive because we consider first that the most of the communities, the microgrid we have to design for that are not so big. Okay, so you know that if is small, it's more expensive due to the economic scale. That is our first consideration. We consider economic scale. The second, about the last time we made an evaluation of LCOE for, I think that only 10 years. Okay, not for the 20 years that it's typically considered for any photovoltaic system. We consider only 10 years, and due to that, we don't consider that we have to that elevate the LCOE because we don't consider the complete life of photovoltaic system. And we consider 10 years because due to the normative of Peruvian normative, if you will replace something big of the project, we have to consider like another project. Okay, so the battery of Lion will be finished in only 10 years. So due to that, we consider the minimum lifetime of battery. But yes, I think that could have to make a change in the Peruvian normative to evaluate better this type of projects, right? But yes, it's we will consider, I think, the 20 or 25 years in our next words together with the 10 years evaluation.
Okay, thanks.
Thank you.
Mona, you had the honor of giving the introduction. Would you like the honor of closing the session?
Yeah, I guess I can. It was a I think very nice session. I'd like to thank to our presenters Luis and Jose, and I'd like to thank my co-host and all the participants who's attended to our session. It was very interactive. I can see a lot of interesting things happening in the chat area, and there's definitely a lot of Q&A which we can discuss more in the Discord, or we can also have a back and forth communication and emails. But it was definitely a very nice session, and thank you everybody for attending.
Thank you.
Thank you very much.
Thanks, everyone. See you all.
See you.
Bye, everybody.
And see you all in the delivery model session next, of course.
Oh yeah, most importantly
Yeah.
to address.
Just a quick word about that. We start in 12 minutes, so you have a break.
Perfect. Okay. Thank you,
All
everyone.
right.
Goodbye.
Thank you. Bye.
Bye bye.